Okay, in this video we're going to cover section 6.3, and that's trigonometric functions of angles. So I just skipped section 6.2 because it's really unnecessary to go through, although there's some homework from that. The what we're going to cover in 6.2 is basically also covers what we're going to cover in 6.3 also covers 6.2. So if you recall, in chapter 5, we defined trig functions there already, and we did this in terms of the unit circle. So let me set this up. So we got, so 6.3 trig functions of angles. So in chapter 5, we did things in terms of unit circles. So we had this unit circle here. There's the two pictures of it. It was, in one sense, it's the traditional two-dimensional object in the plane, and in another sense, it's really just a one-dimensional object if you're confining yourself to the circle. If you're just a person living on the circle, things are one-dimensional. You only can move around backwards, clockwise or counterclockwise on the circle. And so the idea was, if I gave you a number, so we fixed a point. This is like the origin, in a sense, or a reference point of the circle. And I gave you some number, positive number t. That was basically a distance you would travel. So if it's positive, you would travel counterclockwise. And so you would travel along the circle and maybe you land here. And then this, of course, determined a point in the plane. So you can project this point onto the y-axis and the x-axis. So this is some point associated to the number t. So this is the x and the y coordinate. And from this, you could define, for example, sine of t to be the y coordinate, cosine of t to be the x coordinate, tan of t to be the ratio of the y to the x coordinate, and just keep going on with the rest of the trig functions. So this is one way of defining trig functions, in terms of the unit circle. But now we want to look at this alternative approach to defining trig functions, one perhaps it's more familiar, but will end up being equivalent. That is to say, we won't get two different sets of functions. They'll be the same. So this is in terms of angles. So we introduced angles already. We already have an intuitive idea of what an angle is. It's like you have these two rays, and then the angle measure is basically the amount you have to rotate the initial ray so it coincides with the terminal ray. That's roughly what an angle is. We went into more detail in the other video, and if you need to see more of that detail, you can go back. So we have some angle. So we have angle P, O, Q. So we're going to call this, we're also going to label this theta. So theta is some angle P, O, Q. And it's just some, it corresponds to some, basically a triangle. Right? So maybe this is theta. This is O. This is Q, and this is P. So this is the angle POQ, and the idea is to put it in standard form, that is to draw an X and Y plane around it. So we can extend these. So this is really the triangle, but we can extend these lines. So let me just delineate this carefully. So we'll extend this here and this here to get an X, Y coordinate system. So now, when you do that, when you coordinatize everything, if you will, this will give you a point in the plane, X, Y. And this will be this point will be at some distance r from the origin. So this is, remember, this is the terminal, this is the initial side, this is the terminal side. Theta is the amount you have to rotate this initial side, so the initial side it coincides with the terminal side, and that's the angle measure. And then the idea is that, well, first of all, r is the length. It's the distance of the point to the origin, so that means r is the square root of x squared plus y squared. And the idea is that we define the trig functions as the ratios at as these following ratios. So here are some. I won't write them all, but because you can go into the book and look at the definition of the reciprocal trig functions. But the idea is that you're gonna define the sine of theta, this angle theta, or this cosine of theta, as this ratio, the y coordinate divided by r. Now here's the connection with the other approach. Now if the distance is 1, if r is 1, that is i.e. if xy is a point on the unit circle, then we get, for example, sine theta is equal to y, and cosine theta is equal to x. And this just is that other approach that we looked at in chapter 5. That is, theta in some sense corresponds to, so if we're in the unit circle, yeah, theta corresponds to an arc length. Remember, arc length is, so arc length is s is equal to r theta. When r is equal to 1, implies that the arc length and the angle really are one and the same thing. They give you the same measure. So if rotating, when you're on the unit circle, rotating by a certain angle, it corresponds to just traveling along the unit circle some distance. And that will, of course, determine the point in the xy plane. And then when r is equal to 1, the denominators here and here, they just vanish. So you get sine theta is equal to y. So if, in this case, when r is equal to 1, theta can be thought of as an angle or some sort of arc length measure. And then cosine theta is equal to x. So they just give you, they pluck out the x and y coordinates corresponding to the point, or they pluck out the x and y coordinates of the point corresponding to that theta value, which can be thought of as either, in the case of r equals 1, can be thought of as either an angle measure, some amount that you rotate by, or some amount you travel along the circle from that reference point. So these approaches are pretty much the same. Although this approach might be a little bit more general, perhaps, because you don't have to confine yourself to the unit circle. You can look at basically look at a point as far as you want, or as close as you want to the origin. Now there is a worry, and this is not like something that you really have to worry about, because I'll just tell you that it all works out. That, well, okay, so you're defining the trig functions in terms of this triangle. This is more like a philosophical worry or a logical worry, something that could, like a concern you feel, it's like a philosophical point or a logical point that could be troublesome. So the idea is you fixed a triangle, you started with a triangle, and then you define the trig functions in terms of this triangle. But what if I chose a different triangle with a different, yeah, or the same angle but a different triangle? Maybe the lengths are longer or something like that, or maybe alternatively just a different triangle altogether. The angle is different. How do I know I'll get the same trig functions? So that is actually a worry, but it turns out that the trig functions are independent of the triangle you choose to define them. And that's a word that comes up a lot in mathematics, actually. When you want to define something, like sometimes you're defining it in terms of something, like you're fixing some sort of object. In this case, the object is a particular triangle, and then you're defining it in terms of that triangle, but you want to show that, or you're defining it in terms of that object, but you want to show it's independent of that object. That is, it doesn't matter what object you choose, like the object from the same category, like the category of the class of triangles. It doesn't matter which one you chose, it will give you the same definition. And this is like we're basically asking whether or not these trig functions are well defined, that they don't depend upon the triangle you choose. That is, if I start with a different triangle, I get a different set of trig functions. And what I'm saying is that that's not the case. It ends up being not the case. So you don't, I'm not sure if that was something you're worried about. If you were worried about that, that's good for you, because you have a very perceptive, subtle mind. And if you didn't, that's completely fine too, because that's something probably completely off everyone's radar. I mean, I know I didn't think about that when I was learning this. So just wanted to point that out. It's not a huge deal for this class. We're just gonna assume, you can prove it, but we're just gonna assume that these functions, trig functions, are well defined, that they're independent of the choice of the triangle. So here, let's look at some properties of these functions that we're just going to assume that are well defined. Let's look at some properties of these. So I'm going to open the book. This is quite a lot to write, and I don't want this video to be too terribly long. So this is the sort of thing we encountered already in chapter 5, like what is the sign of these functions? And so from the very definition, we can determine it. So we have the first quadrant, they're all positive, none are negative. And that's because in the first quadrant, so remember, this is the definition right here. These are the definitions right here. In the first quadrant, your x and y coordinates are both positive. And the second quadrant, sign is negative because your y coordinate is negative. So sine theta is y over r. R is always positive. So what's going to determine the sign of sign, S-I-G-N, of the sine function or any trig function is going to be, or the sign of the cosine and sine is going to be the numerator. So hopefully that's not confusing. I'm using sine in two different senses, but two different words that sound the same. I can't recall what those are called. But anyways, I'm using sine, S-I-N-E, for the trig function, and then sine, S-I-G-N, to refer to like whether it's positive or negative. So in the second quadrant, sine is negative because, sine is positive because the y coordinate is positive, but these ones are going to be negative because the x coordinate is negative. So cosine will be negative, secant will be negative because it's reciprocal of cosine, tangent will be negative because it's tangent theta is y over x, and so x is negative, and then cotangent is negative because it's just a reciprocal of tan. And I won't go through the whole table, but you can go through the table and just similarly argue why certain trig functions are positive or negative depending upon where you are, in what quadrant you're in. You know, when I give you a theta, you basically are rotating part of the positive x-axis, and it will land in some quadrant. And then so when you take a trig function of that theta, it's going to depend upon what quadrant you are in. The sign is, that is S-I-G-N, whether it's positive or negative. Okay. So there's a couple examples. I'm not going to go through them. They're not terribly difficult. I'll leave these up to you, but I just want to talk about, the next thing I want to talk about is reference angle. So this is going to help us calculate some of these values. this notion of a reference angle. So the idea is we start with some angle in standard position. So theta is some angle, standard position. And then you have the reference angle, which we denote as theta bar. So theta bar, and that's associated to theta is the acute angle. So the reference angle is the acute angle formed by the terminal side theta and the x-axis. So let's draw a picture. Let's just draw a picture to figure out what's going on. No. So I have my XY plane, and then I'm imagining that the x-axis is being rotated by some angle. So this maybe going to be rotated here. Actually, let me just draw the line first. And so then it's rotated this way. So this is theta right here. This angle right here, this is the acute angle right here. This is going to be theta bar. So that's basically all it is right there. So it's this angle right here that so this is your x-axis is always the initial side, and then you rotate at some angle. So this is the terminal side. You rotate it by some angle theta, and then theta bar is just going to be this angle right here that the terminal side forms with respect to the x-axis. So sometimes the angle and the reference angle will be the same. For instance, if you rotate the initial side to some position in just the first quadrant, then theta and theta bar will be equal, but in general they might not be equal. Okay, so let's look at an example. So this is example 2 in the book. We'll just do part A. And the question is to find the reference angle of the following angle. So first we have to determine what quadrant this so we were going to rotate the x-axis by this angle, and then we got to find out in which quadrant does it lie after we rotate it. So to do that, we had to compare this angle with some known angles. So first of all, 5 pi over 3 is less than 2 pi. That's pretty clear to see. So 2 pi is also the same thing as 6 pi over 3, right? And so if you make the denominator just a bit smaller, so if you change 5 to 6, you'll get a smaller number. So that's why this number is less than that. But it's also not too difficult to show that this number is also between 3 pi over 2. Hence, we're looking at the terminal side So let me just say that the terminal side, hence the terminal side is in the fourth quadrant. So let me draw that. So we rotate it, and we rotate it like this. So this is 5 pi over 3. And this will be, so this is theta. So this angle we rotate is theta, and this right here is going to be theta bar. So to get this angle, we just got to subtract theta from 2 pi. And then this 2 pi is the same thing as 6 pi over 3, and then so that it's clear that this is actually just going to end up being pi over 3. I'll let you, if you don't see that immediately, I'll leave it to you to do that arithmetic. All right, let me do one more example and then we'll call it a day. So this is example 4 in the book. And I'll just do part A. So we want to calculate sine of 16 pi over 3. So we're going to do this by first finding, so 16 pi over 3 is actually corresponds to a couple revolutions. So we need to first find a coterminal angle and then a reference angle. So the idea is 16 pi. See if we can do this. See if I do this right. So this will be 5 pi. That's not what I want, though. See if that works. Oh wait, I see. Okay. Determining the coterminal angle is just really a matter of there's no special technique. It's just you have to get comfortable with the numbers and decomposing them in a certain way. So what I'm going to do is take 16 pi and I'm going to write it as, I'm going to rewrite the numerator as, this should be pi. It's going to be 12 pi plus 4 pi divided by 3. So this is, right here, this step shouldn't be mysterious, nor should this one here. And what I'm going to do is now divide 3 into both pieces in the numerator. So 3 into 12 pi is the same thing as 4 pi. And then we have 4 pi divided by 3. So this right here, this number means that, so 4 pi over 3 means you rotate some number. You rotate the x-axis some amount. And then the 4 pi means you rotate it basically 360 degrees twice. So you just rotate it about the whole circle, or rotate it around all the way twice. So you land back at the same spot. So this right here is coterminal angle. So what that means is sine of 16 pi over 3 is the same thing as sine of 4/3 pi. So calculating this reduces to calculating that. Now we want to find the reference angle. So we found the coterminal angle to simplify this, because this is a large angle and it corresponds to revolutions around twice, which will land you back at the same spot. But now we want to find the reference angle. So we have 4 pi over 3. And again, you had to be familiar with those 4 main or primary, I don't know how to describe them, just those 4 angles. There's like reference angles. You have 0, pi over 2, pi, 3 pi over 2, and 2 pi. So you got to compare this number with those. And if you do, you'll see that you see that 4 pi over 3 is greater than pi, but it's less than 3 pi over 2. So that means that the terminal side is in the 3rd quadrant. And so if this is theta, so theta is equal to this implies that theta bar is going to be pi minus 4 pi over 3, which is the same thing as sorry, it's the same thing as, no, this is not right. I think I left something out of the definition, maybe. Okay. So it's got to be positive. I'm sorry. This is an acute angle, so it's an angle between 0 and pi over 2. So this number can't be positive. So I just got to flip the numbers around. So it'll be 4 pi over 3 minus pi, which is equal to pi over 3. So now in the 3rd quadrant, sine is negative. So what that means is that when we take sine of 16 pi, it's going to be, which we already determined, equal to sine of 4 pi over 3. But then I got to tack on a negative number because the sine of it is negative. So then when you do that, we're also going to use this reference angle in this step. So we get sine of 4 pi over 3 is equal to negative sine pi of 3. And this will be finally equal to, you can either use the methods in chapter 5 or you can use the methods that we've been learning in chapter 6. You can calculate this actually, and it'll be negative root 3 over 2. So yeah, the final answer, so this will be equal to negative root 3 over 2. So that's all for this section. I mean, there's some other parts to the section, but I don't think they're really that relevant. So let me stop sharing my screen and end the video.